The last session, the last talk for this morning afternoon session is by Nuno Pesana Santos, model-based object tracking. Welcome, Nuno.
Hi, Atira. Hi.
Hi, how are you?
Special compliments.
Thank you. Great to see you.
Uh, I will share my screen,
Yeah, sure.
and I think that everyone is seeing the screen.
Yeah.
Okay.
Yes, it is visible.
Okay. Good afternoon to all there. My name is Nuno Pessanha Santos. I'm here to make a little presentation about model-based object tracking. I will specify a little bit to UAV applications. I think that is more interesting, probably to give a more practical perspective of a specific problem like this. I will talk a little bit about the motivation of this problem, why we want to make the UAV tracking, the standard problem formulation, key challenges, just to give an overall idea of this problem and how and how we can solve this problem. Okay. UAVs. Nowadays, we have UAVs are everywhere, as stated there. We have commercial off-the-shelf UAVs widely deployed daily. The modern conflict zones, as we all know and see in the news, have speed up the technological developments, mainly the low-size UAVs that are easier to build, to construct, and harder to detect. When we compare fixed wing with rotary wing, of course, we have advantages from one and other, but mainly the fixed wing, like the one that we are seeing there at the bottom left. We have more endurance and can make longer missions. We have a problem with this kind of UAVs because are harder to the takeoff. Sometimes it's harder and the landing, and most of the accidents occur during these two occurrences. But it's a good problem to solve, or important problem to solve, because security, trajectory optimization, and so on. What do we have normally? A camera, a tracking algorithm. And we normally or typically, we do not use in this kind of problem, or try not to use in the majority of the problems, other sensory information, or try to rely at least as possible, because in some applications, radar and GPS are vulnerable to jamming. And if you rely in this kind of data, if you have jamming, all the operation is compromised. If we are talking about a small size UAV, the radar requires a large payload and it's not easy to install. When we are talking about processing and algorithms and this kind of stuff and model-based tracking, we want to have at least acceptable processing power. So all the processing, it's easier and advantageous to make the processing in a ground control station. So we can use UAVs, commercial UAVs with simple autopilots and so on. The standard problem formulation in this kind of problems is the standard problem formulation. We have the camera parameters. We want to estimate the UAV pose normally, as in any other robotic problem. Okay, the translation, the rotation, the angular and linear velocities. It's the standard. We can assume that UAV follows the constant velocity model for the temporal filtering, but we can improve it. But we can follow the standard procedures for any robotic problem. The only difference here is that in this kind of applications, we try to use the UAV model that is critical for model-based tracking to give us offline or online information. We use the model to make a data set or database of possible poses, to retrieve some information offline that we can access during the estimation, or we use the model in real time with all the problems that it may have, like the needed processing power. Okay. The key challenges of an outdoor environment are not different from any other outdoor environment. It's easy to understand that the initial detection is very hard because we have the sky, we have an environment, and it's very hard. If you are talking about a small size UAV, we have limited image information at far distances. It's not easy. Sorry for the sound. And in outdoor environment, we have lots of variations in the environmental conditions. Okay. How we can solve this problem? How can we use model-based pose estimation, the UAV model, the object model, to try to solve this problem? Okay. Some classical approaches, you started to use the edges of the model to compare the reality, that what we are seeing, currently seeing the image with the model information, try to combine that in an error that can be measured and adjusted to try to estimate the pose. And then we can combine multiple data sources, as in any field of any of these fields or applications, and try to combine edges with key point matching. As much information as we can retrieve from the images, as the vast majority of you may know, in the vast majority of the cases, it will give us better estimatives or not, depend of the noise and and our specific application. More recently, deep learning is taking the field. We have some applications that make object segmentation and then use convolutional neural networks to predict the 3D poses from the 3D bounding box in the left side. In the right side of the slide, we have here a database, here a discrete code offline. The model is used to retrieve some previous information that then is used during the estimation process. Basically, all the approaches are different, but the vast majority make the same things. Use the model to retrieve information a priori, or use in the code book, in the database, and then in the estimation process, retrieve or not, because of the need to achieve real time. Sometimes this is a compromise between real-time processing and the use of these methods, and the methods must be adjusted. This is an example of deep learning approaches that use the model to retrieve templates and then compare with reality. These examples here are not extensive. I will not talk about them extensively. I can share the slides in the end. There's the reference there. It's only to give an idea how this is made today. Basically, this is the methods that are appearing normally, and as any field, are combining several processes or several applications that work well, like RAMSAC, like 2D point correspondence with deep learning, and then stack all together to try to have a framework, a global framework that achieves a better result. Okay. As we started as the processing power is becoming higher and available, all these processes become more complex, or at least at a processing perspective, processing power or processing capability, and so on. In this specific problem, okay, let's give a practical perspective of an application. We have a camera, a ground control station, outdoor environment, and we have no other sensor information. Okay, that's a video from some real tests that we made. How can we solve this? We me and Professor Alexandre Bernardino are working in this from the past years with students, myself. We divided these in some stages. We first, because the search area is vast, we want to detect in the image the UAV to try to not to use the information that is not useful for our estimation. Of course, we have a degree of confidence in this detector, and we must use temporal information to try to have the better estimation as possible. Then we try to make the pose estimation of the single frame. We can make optimizations of the frame, multiple architectures, and then the standard temporal filtering as applied in any field. Okay. Okay, we have implemented that structure in the Monte Carlo method, where each particle, where each particle is treated as an individual projection or possibility of pose. Okay. I don't know how to. Okay. Sorry, I just put the laser here. As we can see here, we have the 3D model, and then we project in the image several hypotheses of the pose, and then we compare that possibility with the real image, and we give a score, and then with that score, we can implement the standard particle filter and try to make resampling process and that kind of stuff. I will not go into deeper detail. I think that is not needed here. If anyone after this presentation want to know more or talk with me, please contact me. No problem. We have the camera. We detect the UAV. Here we have a pre-trained database where we estimate some poses to be that compare with the real image, and then since we are making filtering, we need to have the actual measurement, and then we apply an individual filtering to each particle. We have, if you want, we have 100 possibilities. We will have here in this application, we will have 100 individual filters to each particle. The only difference here is that we apply instead of the Gaussian noise, the traditional Gaussian noise, we use some the Bingham distribution. That is a distribution that is defined directly in the hypersphere. It's better to represent circular statistics like the orientations. Okay. What this brings us, we have developed here a little tracker. The only problem in this kind of applications is that it's very hard to obtain fixed wing real data with ground truth. Like the example that is there on the slide, we do not have ground truth for this example. The sensor synchronization is very difficult. It's very difficult to have a time opportunity to gather real data. It's not easy. It's easier to work with traditional quadcopters that everyone can buy. Fixed wing is more, have lots of limitations, but the vast majority of the interest it is in the fixed wing application, since they have more endurance. And they are more appropriate for longer missions that the vast majority of the industry or even the military applications want. It's to have more endurance, more time on the air to be able to perform surveillance missions or that kind of applications. We are trying to improve the simulator with Unreal, with me and Alexandre Bernardin, trying to develop a real simulator that incorporates the aerodynamic coefficients to try to to help us to develop better methods. Other developer tracking approaches that we are working on that are not based specifically in the model, but we cannot try the harder ones without the easy ones. The standard stereoscopic vision, to try to estimate not the pose in this case, but only the position of the UAV on the frame. This is a master's student that I had in the Portuguese Naval Academy. Recently, we have an internship from the Institute Polytechnic from Paris, from France, that started trying to make UAV tracking with a neuromorphic vision, like an event camera there that only gives information from the pixel difference with a certain threshold. We started to work on this. I think this is a good application to combine with a standard camera due to the high frame rates to try to have a better estimative. Other applications that I am interested, it's the autonomous landing in some naval ships, in some ships or other moving platforms. We are working this. This is a different application because the camera is not in the ground, but in the UAV. But the processing is made on the ground control station. And in the future, I am trying to incorporate, instead of using Monte Carlo or only the detector, I'm trying to incorporate the deep learning with model information, but I didn't have the student yet, to the right student to try to make this. Many thanks for your attention. It's only to give a broader perspective about the model-based pose estimation and try to give more info about this specific subject. Many thanks.
Okay, thank you very much, Nuno. Any question? Question from the audience?
No one likes this stuff.
So
It's the
yeah,
last one. It's the last one. The last one is always the
last one.
it's always the best one to make because everyone wants to to go to go home.
Okay. So yeah, one question from my side. So you are using Unreal Engine for the simulation?
Yes. Yes.
Okay, we have, because we are also doing some defense related project here. We have been for the sonar image. For the sonar image, we have been using Gazebo simulator, using some CAD mechanism beforehand, self CAD, then combining on top of Gazebo, and we are going to give a demonstration session tomorrow morning. But that may be too early for you to join, though. I guess.
No. If you send me the information, probably if I cannot be present, the student.
Yeah, we are recording all the sessions, even if you are unable to join us.
Okay.
We are recording the sessions. We will try to
Okay.
it through. Yeah, we'll send it through.
No, yes, it will be interesting because Unreal does not have many available information to try to configure.
Yeah.
It's very limited in the documentation, and it's not easy sometimes to make this kind that seems easier to make a simple simulator only with the equation, but it
made a simulator called S3 simulator. S3 simulator, which is side scan sonar simulator. And we published in ICPR last year. So we are in the process of making it publicly available. It's one of the first synthetic sonar simulator in the field.
No, yes, I have retrieved some sonar data with the real.
It's very hard to get, yes.
With the real USV, but with synthetic data, it's not. Some papers show some synthetic data about sonar, but a simulator that is publicly available, it's very very good for the community.
We did that, and yeah, it's on the way.
Yes.
So thank you very much. So with this, we are winding up today's session. So I extend my sincere gratitude for making this the first day of this workshop on vision for robotics a truly insightful and informative experience. We especially grateful to our resource persons from IST Lisboa, Professor Jose Santos Victor, and Alexandre Bernardino Joao, Plinio, Catarina, Rita, Miguel Texera, and Gonzalo, and Nuno Santos, for all of your very valuable talks. Thank you very much. And your clear explanations and engaging video demonstrations on topics like active vision, then saccadic motion, human robot interaction and grasping, then computer vision for health, stroke rehabilitation, and object tracking. All of this have left us with a much deeper understanding of this rapidly evolving field. Also to our participants, our faculty members, research scholars, and the students, thanks for your enthusiasm and active engagement, which has made this session a dynamic and productive one. Keep the spirit for tomorrow as well. We have a more live demo sessions for tomorrow. Your thoughtful questions enrich the session, the learning process for everyone present. Thank you very much, and see you tomorrow morning. And I'll be, as I promised, I will be recording and sharing all these sessions to you as well. And yeah, tomorrow afternoon, the same time, we'll be resuming the session, the Portuguese session. So I'll have a quick yeah, I'll give a quick plan for tomorrow's workshop. So in the morning from our end, from the host institution, we'll be having a session on gazebo simulator. As I was telling, this S3 simulator that we are going to show with the demonstration. Then after this, we have ROS rover, both simulator and the demo with the robots at the robotics lab. Then Nano robot. We will be demonstrating the Now robot and Auto. And in the afternoon, from IST Lisboa, we'll have Now for Therapy of Autistic Children by Laura Santos, and NVIDIA Exactly by Manuel Serra and Nuno Duarte. So this is the plan for tomorrow. Stay tuned and see you. Bye-bye. Have a nice evening.
Bye. Bye.
Bye-bye. Thanks for everything. Bye-bye.
Yeah,
Take care.
thank you very much.
Have a nice evening there.
Good to see you,
Bye-bye.
Akira, again. Thanks a lot. Bye-bye.
Thank you, Professor Yan. I coincidentally remembered something, Professor. Today marks my defense anniversary.
Ah, okay, really?
September
Wow.
11th, yes.
Okay, so it's another motive to celebrate. Very good. Fantastic. Congratulations.
Viva Lisboa.
Okay.
Miss Love.
All right.
Okay,
Take
bye-bye.
care. Bye-bye. Cheers. Bye.
Bye-bye.
Bye.
See you.